Hello, hello, hello. Okay. So let's start the session. So today's session is about binary search implementation variations. You could say that how differently you can implement this while loop and all the stuff related to that. So most of you might have participated in lead code contest and might have seen different codes. And I guess at least for me, when I was newbie, I was confused like why people use certain things, and I didn't understand most of the things of that, and I didn't even bother to learn that at that time. But when I joined Google, I saw one binary search code, uh, and at that time they were using some different variation of binary search. Even though I knew that like the core logic of binary search, but I was like at that time I was little bit concerned that I didn't knew these things, even though I know so much stuff, but I never bothered to learn about this. So at that time I kind of like tried to find every stuff related to that, and hence the motivation for today's session is also that you guys should also know what different variations are there. So at least in interviews, when interview, like, it's high possibility that your interviewer uh, uses some different variation of binary search and he tries to understand your code, right? So you can explain with much ease if you understand all of this stuff. uh, it kind of like reduces your communication gap with the interviewer. Like it happened with me also, like uh, when in my fourth last round in Google Warsaw, right? So there was an search code. It was kind of like the first wrong commit, but like based on the NR machine or something like that. But he was trying to understand my variation, like while the common template variation, this one. Like we are used to this stuff, right? Like I guess I don't know why I started using this, but I'm so used to this template that I use it everywhere without even second thought, right? But he was trying to go into much detail that how my while loop is working, because he might be he never seen this template. So he was confused why am I using this, and I had to explain that at that time. And it is very common that this stuff happens, that how these pointers are moving, how this answer, we are marking the answer, right? But anyway, so that's the point, and our goal for today, that we should understand every permutation combination of this. L is less than R is I have covered most of the stuff, but we will start with what's the most common bug, you could say, with binary search. We start with the bug, then we will do the reverse engineering on that not reverse engineering, but reverse construction on that, basically. So let's say pen stopped working. Okay. So most of there are like two types of binary search bugs. One is like the L plus R divided by 2, which goes to overflow issue. And this is very rare, by the way, even though people consider this L plus R minus L by 2 stuff like this, it's mostly useless, because most of the binary search problems can be solved by this one. You don't need to do this, because it's rare that you will get the value with that it will overflow, right? Because most of the cases it's around 10 to 9, and 10 to 9 plus 10 to 9 divided by 2 is still like 2 to 10 to 9, which is still less than integer range, right? So it doesn't overflow in majority of the cases, 99% of the cases. Yeah, rarely I have used this stuff, but there might be some virtual functions, what are virtual functions that uh, So basically it's a range mapping between minus infinity to infinity, and you are constructing that and binary searching on that. Minus infinity could be minus long max and something like that, and long max. So if you are binary searching on this big range, then not long max, but basically better border, like minus 10 raised to 15 to 10 raised to 15, let's say, which is greater than integer range, but still manageable. Like if this added two times, which is still greater than long max or less than greater than long mean, but less than long max, something like this. Anyway, so most of the cases are like this. The purpose being that this, not this, sorry, this one is useless, and this one is useless. You can just blindly use this most of the times. It doesn't matter, right? Like, but you at least you should know that how to take care of the overflow. Why it doesn't overflow in this case? Because let me write it as a first book. First common bug, which is the overflow issue. Overflow issue, first common bug. This is the one, and the second one, which we will discuss, which is infinite loop. There is also one person who mentioned in queries that they face difference of one, but I guess it's more of the understanding of the concept logic, not bug basically. This is the infinite loop. By that logic, infinite loop is also the concept of. Okay, so this is the one. Blindly go with this L plus R divided by 2. No need for this one, L plus R minus L divided by 2, because it might be possible that L is negative and R is positive, right? So when L is negative, in that case, it will still overflow, right? So it doesn't guarantee that uh, our implementation, or like the mid part like this, is safe. It is not always safe. If you want to be a safer option, like 99%, 99, I will not say 99, but let's say 97% to be that I won't be wrong. 97% cases this works. We don't need to take care of. But if you want to be more safe, you can use midpoint. This is available in C++, midpoint L comma R. I guess C++ 20 or 23 or 7, 20, I guess C++ 20 around. Midpoint was announced, and you can use this as a midpoint. It will give the midpoint function, right? Uh, so let's discuss more around this, around the midpoint section. Uh, what's exactly the midpoint? What's the time? 9:44. Okay, midpoint. So basically, if you are given L comma R, if you are given this range, the midpoint is basically this. If you plot this on x-axis, L R, it's basically the center, right? But usually what happens is we deal with integers here in programming, right? We don't want to deal with decimals, because the first thing you do is like int mid is equal to L plus R divided by 2, right? So this is integer, this is integer. So obviously the operation uh, derived from this should be integer. Uh, if you want to derive it as a double, you can just multiply it by 1.0 and then do something like this. So it will start with it will store it in double operation, and then consider chain everything as double and try calculating it as double of mid. This will also work. But the rounding part is very different in double, so don't use this thing. If you wanna like int mid, if you are using this instead of double and still using 1.0, the rounding part will get weird, so don't do that. You can just use double mid. Okay, L plus R divided by 2 is the common variation, and this thing. So we deal with mostly integers. This is our deal with integers always. Why? Because compilers are fast with integers as compared to double values, because double operation are slower, right? I guess so. Double operations are slower, right? And integers, integers are kind of faster. You might have learned in this in your computer organization and architecture class. Okay, anyway, that's not our concern. So L plus R divided by 2 is the midpoint, but not necessarily that this might be an integer, because as you can see, if my range is, let's say, 4 comma 9, right, and I calculated the midpoint comes 4 plus 9 divided by 2, which is 13 divided by 2, which is 6.5, right? 6.5 for 4 and 9, and I don't want this to be 6.5. I just want to make sure that my algorithm is always dividing it in half. I don't care about this 6.5, it is 6.5 or 7. I just need a sufficient algorithm that my search space is reduced to half at least, right? So what we usually do in programming, so you might learn this formula also, which is, if you wanna um, declare n, it's n by 2, which is floor value plus Ceil value. Ceil value. This is the formula. You could remember this, very useful one, right? And there are also multiple identities associated with it that you could also learn to improve in programming. But anyway, so 6.5, all we do is, because our target is the log n complexity for binary search, right? So all we need to do is divide this search space into half. That's our main goal. So we don't care if we are doing it to via Ceil or floor, because iteration wise it doesn't change much. At least there would be one iteration difference depending on where the our bound lies on it, whether it lies on this side or this side, or wherever it lies there. The iteration difference, iteration number of iterations difference is not much. Okay, our target is the complexity, which is log of n. So exact number of iterations we don't care. I will also tell why we use L by 2 plus R by 2 is also safe sometimes. Okay, anyway, like, so I don't want to confuse you guys. Okay, so log n, our target is this thing that we want to reach this. So the binary search, in binary search, all we do is meet L plus R divided by 2, which is the floor value, always, right? Mostly, right? You can also use Ceil value. I will tell you when you wanna use Ceil value, which is this thing. If you wanna calculate the Ceil value, like in programming, when you are dealing with positive integers, when you do x plus y divided by 2, like int mid is equal to x plus y divided by 2, it automatically calculate the floor value. You should remember that. So any integer division is kind of like floor value. What's floor value? Floor value is basically, if you divide, and if you divide, it gives you the integer part and neglects the decimal part. Like integer part x point zero zero, whatever, this part is neglected, and you will be given not x, I could say different variable, the decimal, not decimal, integer part. Just integer part plus decimal part, right? When you divide something, you get like this, but it uh, reduce neglect this part and just gives you this part, because there are faster algorithms to do this. It doesn't do it via normal division method, that the first number and multiply by 10 and divide by that and blah blah blah, blah. They don't do that. They all they do is via different division algorithms. and those are like parallel operations. uh, okay, so integer part we get here via x by 2 always, right? So it will always be rounded down to the nearest integer, right? And by the way, there are like different bugs associated with it, because when you deal with negative integers, the floor value calculate differently. But uh, but normal floor function definition is different for negative values, so remember that. But I'm assuming it's a positive for now. So int made equal to x by 2, right? uh, any number you could say n instead of x square plus 5 by 2. Okay, so uh, all we need to do is convert this to floor value, right? We don't need to do that, but like our computer does. So it will be converted to floor value, and this is our uh, this will be okay. So where will we deal with integers, midpoint, double. This is relevant, not relevant. Mm, 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 Six. So I was trying to say where we were on uh, the first common bug, which was the overflow issue. Where were the overflow issue? Okay, we discussed that thing. Now we only need to care about the infinite loop. Okay, so now that you understand, see, okay, I forgot to add this floor. I explained the floor value. Let me add the title here. Floor value, Ceil value. So Ceil value is basically just the upper portion. Now to handle the boundary extra cases, what they try to do is something like this. I add -1 to that. Sorry, +1. Uh, the general definition for Ceil value for this is x plus y divided by r, or any n divided by r is basically x plus y plus r minus 1 divided by r. So it basically means whatever this value is here v, and so it means this is the boundary that it needs to touch, right? So the moment it touches this, it should add +1. So r minus 1 is the limit that it will not push it to the next boundary. It will always keep it here at least. And the because integer division gives you the nearest integer, so whatever value is here, it will push maximum until here. It will never push it to the this boundary. So you will get the first integer that is greater than this one, right? So hence that's how the Ceil value works, right? So the moment you do 5 divided by 2, you will get 2, and 5 divided by 3, you will get 3 value. Sorry, I wanted to say 5 divided by 3 is 2. No, no, sorry. Hmm. So nice. 5 divided by 3, 1. 5 divided by 3, which is 2. Okay. And similarly, 5 divided by 2 is 2. And 5 divided by 2, Ceil value is 3. Okay. So any integer can be represented as the floor and Ceil sum value. So our purpose here is to understand first the floor and Ceil value, then understand why we can use this to deal with various bugs with binary search. Okay. The infinite loop thing. Okay. So mostly the infinite loop occurs like you can use like there are various implementation here. You can see this midpoint calculation, right? You can use anything l plus r divided by 2, l plus r plus 1 divided by 2, l plus r minus l divided by 2, l by 2 plus r divided by 2, right? This is the common thing. This is the Ceil portion, this is the overflow portion, and this is the fancy one. You can use any of them depending on scenario, but okay. So the when is the infinite loop occurs, like plus one bit two. Let me write it again for you. What was the third one? I forgot. What's the third one? Acha, overflow one. Okay. L plus R minus L divided by 2 and L by J plus R divided by 2. Okay. Infinite loop. So we'll start by understanding. This is the most important part. Overflow one is the common one. You will not face that much. You will face mostly the infinite loop, and this is the important portion here. So let's start with a small construction. So let's say our range is restricted to only one number, right? Like let's say L comma L. In that case, we know you can easily calculate our answer. After that, if let's say our range is reduced to two numbers, obviously it will reduce to one number depending on your implementation. If it is while r minus instead of if it is this r minus l less greater than 1, obviously this is the if this is the invariant, it will stop when r minus l equal to 1. It means r is equal to l plus 1, right? So our range will never get to l comma l in this implementation, but when you choose l is less greater than equal to r, in that case it might be l comma l, right? Or l is greater than sorry, l is less than r. I'm writing hold up 1 second. L is greater than equal to r and l is less than r, something like this. So this will stop when l equal to r plus 1. This will stop when l equal to r, right? This is the valid range, this is the invalid one. The all we are trying to understand when the bug occurs, right? Now let's say we are at 4 comma 5, right? Our l is 4 and our r is 5, the simplest case, right? Or you can put any even odd number here. It's very symmetrical. Like you can use choose x comma x plus 1 and you will deal with the same thing mathematically, right? But because okay, anyway, like I will not choose x comma x plus 1. You can try it yourself, but I'm just choosing 4 and 5. Even if I chose 8 and 9, I it will give the same result. It doesn't matter. So L equal to 4, R equal to 5, right? After that, what we will try to do is 4 plus 5 divided by 2. So what will happen in this case? It will always go towards 4, right? It will go towards the smaller number because floor is the smallest number, which is smallest number, the integer portion basically. So 4 plus 5 divided by 2, which is 4, or in another words it is basically 4 comma 5 ka mid wala portion, and it will choose the nearest integer part. Another interpretation of this, so 9 divided by 2, which is 4, right? So it will always choose towards 4 and it will never get towards 5, right? So if your implementation is something like this, that when you are at 4 comma 5 and you are let's say your predicate, I should also explain the predicate definition first. I will explain that, but just assume for now this as array, and 1 2 0 1 2 3 4, this thing. No, no, sorry, 4 comma 5. So this is 4 and this is the fifth index, right? So all we need to do is find the first one. Obviously we need to find this boundary, right? The partition point here. So because there is no use for finding the rightmost one or the leftmost zero. All we need is the first zero or the first first rightmost zero and rightmost zero or leftmost one. You can use anything for that. Everyone is comfortable and understanding everything, right? Or am I complicating too much with maths? Sorry, I am not checking comments. 1 second. Can you explain this one example? Which one, bro? L plus R minus 1 by R. Acha, okay. The Ceil portion, you mean divide by 2, right? L plus R minus 1 divided by 2. Okay, you write the comment until then. I will just complete this portion at least. Okay. So, let's say my implementation is something like this. My predicate was the same thing, which is the 5 zeros and then 1 1 1 1 1, or my array was something like this, and I need to find the last zero, right? Using binary search, last occurrence of zero. The indexes are 0 1 2 3 4 5, right? So what happens in most of the binary search is your range will be divided, and in the end it will always end up at 2, right? Like even if you started with 0 and whatever the number here is present, let's say n, right? So it will always be searching the space, shrinking the space basically, and you will always end up at two numbers. It will never happen that it will never happen that you will get to 3 and then directly to 1. It will always be the case that you will always reach to two numbers. Like it's mathematically impossible that you will skip 2. Why is that? Because let's say any number, so it goes to n divided by 2, right? Okay, I will not go with the proof. We can go it later, so else we will waste too much time in this. So 4 comma 5 we need to do, right? And so in the end, all you need to do is we will reach two number, and that is the infinite loop ka culprit. We will always reach two numbers. So you can avoid the infinite loop at exact this point, that the moment you reach two numbers, you can just record those two numbers, right? You can just record those two numbers and just end the loop here and get hence most of the people try to choose this while r minus l, because what it does is basically it stops when r equal to l plus 1. What does it mean? That you will stop at this range, two number ka range, right? So the moment you stop your infinite loop ka culprit. But there are many variations or binary search that people use, that while l is less than equal to r, l is less than equal to r, l is less than r, l is less than equal to r, then they try to do r equal to mid, right? Some people use okay, first let's try to understand this thing, then I will explain that how different implementation introduce that bug. Okay, so let's just select one implementation for now, which is what would be the implementation here? Just giving fine, and we should never reach the 4 basically now. Okay, I will try to construct the bug here. Uh, Basically our bug is whenever we go to 4 comma 5, we will never reach. So first thing, this is not our implementation, because if this was our bug will never occur. So let's assume that our implementation is either this or this, right? So Let's call this thing L is less than R. The moment we do binary search, the moment we reach at 0, uh, 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 our pointer movement should reduce it by 1. Here it is L equal to R, and in the end it should store one answer at least. So my implementation I will choose is L equal to mid, R equal to mid, L equal to mid plus 1, or mid plus 1 will take it here, right? So I will choose L equal to mid and R equal to mid, let's say. The moment I choose this thing, it will never ever increment the boundary. Acha, that's the bug na. We will never increment the boundary. Okay. In this case, we will never increment the left part. Or in another word, we will never shrink. That's the, if you wanna try to find the counter case, corner case, this is the one. That if we can't shrink our range, which was 4 comma 5, if my range is always 4 comma 5 to always 4 comma 5, the in the next iteration, then that is the infinite loop bug, right? So how I introduce this bug, I chose that this L ka portion is always 4 to 5, right? Uh, or or you could say that the moment I got 1, yeah, you could also do this thing. L equal to mid plus 1, R equal to mid. The moment I calculate, but no, that's a Ceil wala portion. Na? This is the R equal to wala portion. Okay. So for floor, this is the implementation. Floor variation, which is L plus R divided by 2. So the moment I did this implementation, any one of this you can choose. L is less than R, L is less than equal to R, it doesn't matter. But the bug, how we introduce the bug, by making the corner case that our range will never shrink. So my L is always pointing towards mid. So the in first iteration, like let's say my range was big and somehow I reached towards 4 comma 5, and my implementation was something like this, right? L equal to mid, R comma mid, like this work flawlessly. Like let's say my range was 1 comma 10, right? And there is some 001 here, something like this, basically non decreasing or increasing for you guys. Okay, so all you need to do is shrink your range, like this implementation, L equal to mid, R equal to mid, right? I will just construct the 10 numbers here. uh, okay, so 1 comma 10 and the one base indexing. So 1 plus 10 divided by 2 in the first iteration, it goes towards 11 by 2, which is 5, which is the fifth number, which is 0. So and okay, I forgot to mention one thing, that when we are not considering extra answer variable here to store what index my answer lies, I will use one of the boundaries or one of the this variables to store my answer. This is the most common variation. This is the most common implementation, that not most common, but I have seen most of the red coders and all those people use this implementation, that they will use one of the boundary to store the actual answer. And I will also go toward that implementation, that when you should do that, but first we will focus on bug. So answer, you can do that thing, but here R is basically storing the one wala portion, and L is storing the another portion for that. Okay, so if you choose something like this, it will introduce a bug in your code. Or I should have done, what should I have done? But anyway, so 1 plus 10 divided by 2, it got to 5. So after that, I add 5, I got 0. I didn't found my index, so I know my index is in front. So I will choose L equal to 5, R equal to 10 in next iteration. From L equal to 1, R equal to 10. And after this, 15 divided by 2, which is 7. Then at 7, I found 1. So it means my range restricted to L equal to 5, R equal to 7. Right? I didn't do any plus 1 minus 1. Just find the mid and assign the mid. Right? And after this, 5 plus 7 divided by 2, which we got toward L equal to 5, R equal to 6. Right? And here, L equal to 5, R equal to 6. Here comes the bug. The moment you reach here, you will get 5 plus 6 divided by 2, 11 divided by 2, which is again 5. And it will start giving you the same value, L equal to 5, R equal to 6. How I introduce the bug? I introduce the bug via reverse engineering that my window will never shrink. How my window will never shrink? By choosing the variable which is the exact same parameter which was before, right? So either if you want to make sure that you will not encounter this bug, all you need to do is always choose L equal to mid plus 1, so that your pointer is moving, your window is always shrinking, right? So if you are using any of this variation, L is less than R, or basically not using the extra answer variable, you should always make sure that your window is shrinking in next iteration. So the moment I did L equal to mid plus 1, it means my bug is resolved. So let's say now this is the same example I can't use, but let's say at 4 comma 5 I got here. So at this point I will not get the bug, right? It's 4 plus 5 divided by 2, which was 4, right? And at 4, the moment I introduce 0, like let's say if okay, R equal to mid, thi- this is the bug resolution, L equal to mid plus 1, else. If I did this thing, the moment I reach 4 comma 4, my next range will be 5 comma 5. Bug resolved by just adding plus 1. How I resolve the bug? By making sure my window will shrink in the next iteration. Everyone understood this thing? Our goal was to reach two numbers. How binary search loop works is it's always shrinks the window. The common sense is like it will always shrink in half, but the bug identification is on two numbers. It will always be buggy on two numbers code. uh, Everyone with me for this? Okay, so I will also write it down here that node always always shrink the window, right? Now let's say how I could have done this by changing not the boundary, but by changing floor to seal. I could have avoided the same bug, because what was happening before, because my range was 0, 0, 1, right? Like it was the increasing range, right? So the moment I did the decreasing portion, in that case, L equal to mid or R equal to mid. My variation was this, na? L equal to mid, R equal to mid. It was pointing towards the floor value, and if I choose 4 comma 5, in that case, 4 plus 5 divided by 2 plus Ceil wala portion will be 5 always. So in that case, it will be 5. Then L equal to mid. Will this introduce a bug? Let's check. Will if this will introduce a bug or not. Plus 4, 4 or 5. 4 plus 5 का range, and it will always again gain to 4.5. It will increase above. I remember one case where we can use exactly Ceil portion, but I don't remember now. I guess I have written in my notes. Anyway, I will add it later. You don't need to do the casework. All you need to understand is the basic thing, because there are so many cases in this and you don't need to remember everything. All you need to remember is always try to shrink the window by making sure that ha, okay, I will show you another portion first. So I have written here in the first part. See, pointer movement. So here pointer movement, you can see I am using extra variable. But if you are not using extra variable, which is answer, which is most people do, the advantage here is you don't need to type extra variable. Your typing speed increases by not typing extra variable. I don't know if it matters or not, but in yeah, like some people might be for some people this might be the preference that they don't need to type extra variable. Okay, so if okay are equal to me, this is this two portion, these two variations, don't use extra variable, which is answer. Don't use don't use answer basically, yeah. And if okay, this is the classic variation, which is the extra variable answer. And now you can see here that this r equal to mid minus 1, l equal to mid plus 1, this portion is always making sure that whatever iteration I have landed, like whether I am getting the predicate as 0 or 1, it doesn't matter. My window will always be shrinking by 1, right? This plus 1 and this minus 1 is making sure of that. But here what was happening, I can't do that because I am using one variable instead of answer. I'm using one variable to store the my bound or answer or whatever the binary search portion you need basically, right? So r equal to mid is basically storing the first one occurrence. So if I do 0 0 0, I will use another color. So if I'm doing 0 0 0 0 1 1 1 1 1, r is storing my answer, right? So if you choose L is less than equal to R, in that case, I guess in that case L is less than equal to R. Let's say this is the implementation. Sorry, this is the invariant, right? This is the invariant. L is less than equal to R. It will stop at L equal to R plus 1, but my R will store this answer. So the moment I got if okay or this value equal to 1, whatever the if mid equal to 1, R equal to mid, else L equal to mid plus 1. Because one of the stuff here is handling the pointer increment, and I'm using the L plus R divided by 2 wala portion. So even though 4 plus 5 divided by 2, 4 is always reducing, this plus 1 is making sure that our pointer is always getting incremented, right? So L plus R divided by 2 is always getting incremented. If mid is equal to 1, okay, so this value, we are interested in this value basically, 1, right? Because all of the binary search, whatever task you solve, right? If you want to solve on the sorted array, let's say if you are like given 1 2 3 4 5 6 7, if you need to find the first occurrence of 1, all you need to do is construct a function on this. That function of x greater than equal to 4 is my, oh sorry, v greater than equal to 4 is my function of v basically, right? And it will give you some value. So for this one it will give 0 0 0 and it will give 1 1 1, and you can easily via binary search you will find the lower bound and upper bound, whatever you need to find, right? So if you do v less than equal to 4, you can also use v greater than 4, and you will get the upper bound of that, right? There are different ways to get lower bound and upper bound. So all you need to do is find the function of v. So predicate is basically the boolean portion of that, whatever the conversion portion is. So the classic binary search is you are given a sorted array and you need to find the value existence, or so what you could do is just find the low is greater than equal to value, or try to find the first occurrence via binary search. Anyway, that's the classic portion. uh, our aim here is to understand where were we? Shrink the window. No, 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 we need to. This is the infinite portion. Stop. Built. Arey, where did my page go, man? Midpoint, first common bug, overflow issue, double mid, infinite loop, x to x plus 1 वाला portion, r equal to l plus 1. Window will never shrink. Or, where is that portion? Equal to. This one is not, and this is then all. Where did we lose? This was one, can which page? Okay, anyway, we don't want to waste time. So infinite loop, overflow issue, and extra answer variable that we need. Where is that extra answer variable on a page that I'm looking at? Acha, here this one. Okay, so this r equal to mid minus 1, answer equal to mid. So if you are storing here in answer, it's very safe option to always store your whatever index you are getting inside the answer, or else you can use one of the variables to store the answer and use another variable to move the pointer, right? So if you get the false value, increment the L pointer, because it means that at midpoint I have no beneficial value, right? So moment I got, let's say there are big ranges of 0, and you somehow landed here first iteration, right? So I know that I need the first one, or this 0, but mostly this first one, doesn't matter. So this 0 is useless to me. I will always go towards right. So what I will try to do is, by taking L equal to mid plus 1, I will always make sure my window is moving forward. L is equal to mid plus 1, and if I landed towards 1, so I could choose r equal to mid, right? So this r, because we are always shrinking the window and maintaining the invariant, it will always make sure that we will always be uh, getting towards here. So my r will always point towards this thing. If you have taken care of incrementing pointer, if you have taken care of the bug that window will never shrink, then you will always land toward this, right? So whatever variation you choose, while L is less than equal to r, while L is less than r, but this will stop when L equal to r. So it doesn't matter whether you choose this or this. All you need is basically this thing, r equal to mid thing, and using this you will get your answer, right? You can also choose another portion that you can use another answer variable, which is initially you can declare it as -1, and declare it as -1, and then kind of use this answer variable to store this portion. So answer equal to mid, and I know if I have stored my answer, so I could choose to shrink my boundary toward left side because I have already stored this answer. So r equal to mid minus 1 in this case. Else L equal to mid plus 1. This will be still the same. Because I am using extra answer variable to store the index, I could be more comfortable and just shrink my space towards r minus 1. Right? You can use either this variation or you can use this variation. But remember that this is increasing array. The moment uh, this you can do on your own. Try to think that what happens if we do something for this type of array, decreasing array, you can say. So for decreasing array, it will, you need to find the first one. So what will you do in this case is basically use the left boundary. If you wanna guess what boundary will store what, all you need to do is just consider this partition case, which is 1 0, and this left boundary will store, and you need to find the one, right? If you need to find the one, your left will be mid. We'll choose the next page. By the way, hence I don't use this way. I always use the vertical orientation because that gives me more space. That is 1 0. I could also derive here, but I choose next page. Okay, I will just write here only 1 0. Let's say I need to find on this kind of array, decreasing array, right? So if I need to find the first occurrence of one, like the last occurrence of one, so you can see my portion looks something like this 1 0, right? So this portion is stored as L equal to mid, and this portion is stored as r equal to mid minus 1. So if I got 1, if okay, or like if mid equal to 1, my L will be equal to mid. So my L will be storing the value of 1. Else r equal to mid minus 1. So you can return your answer as L. You can return your answer as L. Now, if you choose your invariant as while L less than R, so it will always stop at L equal to R. So in this case, you can also use R here, return R. But if you chose while L less than equal to R, so in this case, what will happen? It will stop when L equal to R plus 1, right? So even though it will stop at L equal to R plus 1, can we use L less than equal to R in this case? I guess we can, but we need to return L minus 1 in this case, I guess. Oh no, because we are storing L equal to mid 1 0. So when we are at two numbers, my floor value will be pointing toward this, right? So if I got my L portion, acha nahi, then it's a bug, na? Because it will always land on 1 0. This is buggy for this portion. For while L is less than equal to R, if we do something like this, okay, so if it is buggy for this thing, it will also be buggy for this while L is than R. Because the moment I got towards this range and it is always pointing toward the floor value, then I will never get the search space reduced. So R equal to mid minus 1, L equal to mid will work, but my search space will never be reduced. Like let's say L equal to mid is 4 and R equal to 5, right? So here 4 comma 5 is pointing towards 4 comma 5. Because all we need is one second. So how could we avoid the bug at the same time? uh, we can maintain. In this case, you can use the Ceil value because it's a buggy, right? And I said that sometimes floor value is useful, sometimes Ceil value is useful. So here in this case, it's L plus R plus 1 divided by 2 or Ceil value of mid basically. So what will happen in this case when we are at 1 0 or basically the index 4 comma 5. So what it will does, it will go towards 4 5 and point towards 5 comma 5. It will not be buggy. The moment you choose the moment you choose 4 5 and the floor value, it will be buggy. How buggy? Because 4 comma 5 floor is again 4 comma 5, but Ceil is 4 comma 5. uh, why it is buggy? Because my implementation is this. My R was responsible for shrinking the boundary, right? R equal to mid minus 1 was responsible for shrinking the boundary, but I was not getting towards R, right? My floor value was always getting towards 4. Sorry, my floor value was always getting towards 4 here, right? So this implementation will not work if I didn't choose Ceil value. If I chose floor value, because my R was responsible to move. You guys might also ask me like, why are we making so much effort? So like, if it is so like likely that we might introduce bugs in this way in this implementation, yeah, I agree with that, but this is to understand how pointer movements works. This is for your own uh, development, not the binary search implementation exactly. This is to understand how bugs can occur in many cases, right? You need to understand why certain decisions you do, uh, why we make certain decisions, so that our implementation is this way. Not just you are blindly following certain implementation and never know how bugs can occur, right? At this point, I have shown you how many bugs can we are facing by these implementations. But anyway, I will also show you when we will reach the common template part. I will tell you two safe implementations. Okay. So floor portion is buggy when you choose this, but the moment if it was certain array like this 0 0 0 1 1 1 1, right, and my implementation was something like L equal to mid plus 1, then in that case floor value is safe, because all I need to do is the shrinking portion. Your thought process should be revolving. If you want to find the bug with that implementation, your thought process should be revolving around that this window is always be shrinking, right? So 4 comma 5 floor implementation was giving 4 comma 5, but L is always pointing toward mid. L is not incrementing, right? So floor and L equal to mid wala part is buggy plus. Similarly, Ceil plus R equal to mid wala portion is buggy. These two combos are buggy. Floor and L equal to mid wala combination and Ceil plus R equal to mid wala combination. So you need to choose the opposite portion, right? So if I'm doing L equal to mid to store the left boundary, you should always choose this Ceil portion to not get with bug. So if you are choosing R equal to mid, you should choose floor one. This because these combinations are buggy. Everyone understand this thing? This is very crucial thing, by the way. You should understand this to why floor plus L equal to mid and why Ceil plus R equal to mid are buggy. If you have any query with this, you can ask to me. Any queries related to this? Why this is occurring? Don't be shy. If you didn't understand anything, you can ask. Nee, double wala portion. I know, I know. Like you have asked the same in the form, right? I will. I guess someone has asked. I don't know if that was you, but someone asked. Someone have asked the double wala portion. I will discuss the double wala portion in the end. First, let's cover the buggy part because now we understood why the floor portion is buggy, L equal to mid, and why seal. So all we need to do is shrink the window, and that is taken care of this thing, right? Because one of the variables is storing our answer, you can choose that thing. We can also modify this portion, but anyway. So these are various bugs. Now we will get toward the safe portion. Uh, this is the bug one. So first common bug was the overflow issue, which we discussed, that you can either choose this, either choose this. You can. This is again the buggy one. I don't trust this portion. I don't never do this. But if you wanna do, you can do this one because this is commonly said that this is safe for overflow, but I don't think so. But anyway, you can choose this one, and else just choose the C++ midpoint. Uh, Floor value, seal value, wala definition. Okay. Infinite loop. We were discussing the infinite loop basically, and the combination, dangerous combination of floor and n equal to me. And you don't even need to remember those cases. Just remember that the L equal to mid should be getting incremented somehow. So if it is floor, so if it is floor, and you can remember it this way, that 4 comma 5 ka mid ka portion, if I chose floor it will point towards 4, and if I chose L equal to, if it is not L equal to mid plus 1, then obviously my code is buggy for the range 4 comma 5. So you can understand it this way. Or if it is a seal wala portion, then my code will always give mid equal to 5, then R equal to mid is buggy. So seal R equal to mid, floor L equal to mid. These two combinations are dangerous. You can remember this way. Basically, always shrink the window. Thumb rule. Now let's jump toward the safe implementation. What are the safe implementations? Safe implementations are basically the one that people regularly use, which is while L is less than equal to R. This is the common part. I also use this one. I don't know if I'm calling this common because I use it, because I have seen this in many portions that I use extra variable, answer equal to -1, L equal to mid plus 1, else R equal to mid, something mid -1, whatever. Like if you wanna, if it is 0 0 0 1 1 1, then if I want to find the first occurrence of 1, then obviously mid plus 1, else shrink the window. 0 0 0 0 1 1 1 1 1. If you need to find the first occurrence of 1, then you will choose the, obviously you will try to move towards the right side, so you will choose that if you got the answer, sorry, while L, if okay, I forgot this thing. If okay, my answer is this after calculation of mid. So I'll store the answer and move. I'll store the answer basically here. If okay. I'm doing something bad here. I have done completely wrong. One second. While L is less than equal to R, if okay, or if the value is 1 at that place, first calculation of mid, which is L plus R divided by 2. Doesn't matter, you can choose anything because pointer movement is safe. So if okay, uh, in this implementation, by the way, you can choose any possibility, which is L by 2 plus R by 2, L plus R plus 1 divided by 2, 1, 2, or the overflow wala, anything. Everything is safe in this implementation. If okay, L, if you want to find the first occurrence of 1, it will be L equal to, uh, if we got the 1, uh, then obviously it is R equal to mid minus 1, answer equal to mid. We will kind of shrink the window towards left because we need to find the first occurrence. Else we didn't find, then just mid plus 1. This is the safe implementation. So if I am here, I will try to go towards right. If I am here, I will go towards, sorry. If I am here, I will go towards left. If I am here, I will go towards right. Right. So depending on that, uh, if I'm trying to go towards right, I will try to shift my left boundary to the next number, which is the mid, and based on that your space is always, search space is always reduced to half. So if you are here, you eliminate this space, you try to go here, try, if again you divide by 2, then you eliminate this space, you try to do here, and in the end there will be only two numbers or one number depending on implementation. So this is the safe implementation, you can always choose this one. But there is also another implementation which is very noteworthy, you could say, which is R minus L is greater than 1. What does it mean? It's basically stops at two numbers. Stops at two numbers because we know our maximum infinite loop bugs are due to at are this thing, right? Like whatever we discussed until now, that if it is floor, then we can't choose L equal to mid. If it is Ceil, we can't choose not equal to R equal to mid, basically, right? Dangerous combo. So most of the cases these are due to the two number case, but the moment I did while R minus L greater than 1, you can choose anything. I will also tell the significance of sentinel values, because but I will discuss that in queries, I guess, because that will save us time. So this is the second implementation, safe implementation. This is also safe. And here if you got your answer, if okay, then R equal to mid, else L equal to mid. As simple as that. No pointer movement, nothing, because I'm just assigning the boundary and storing the answer. Here R is my considering the predicate to be something like this one, right? So if I got my boundary as R, I will choose if okay, R equal to mid, else L equal to mid, right? So here when because I know my boundary or my for loop or while loop is stopping at two numbers, I will always end up at this case, right? In the end scenario or final scenario will be this, that L will be at this pointer and sorry, this index, and R will be pointing at this index, L R, two number case, because we are stopping at two numbers and it will never be an infinite loop. So this is also safe implementation and simple implementation, right? Instead of this, here we have to maintain extra answer variable and do the pointer movement. Here we don't need to do that. Just stop at two numbers, R equal to mid, L equal to mid. That's it. You can choose any floor, Ceil value, because uh, what's the I guess the floor value, the L by 2 plus R by 2 wala portion was Buggy in 567 na? So let's say 5 divided by 2 is to 7 divided by 2 is 3. uh, in this case, which is L equal to mid, R equal to mid. This is the Buggy portion. So someone asked me why, what are the advantages of using L by 2 plus R by 2. So L by 2 plus R by 2 is useful if your pointer movement is always plus 1 minus 1, which is this implementation. So L by 2 plus R by 2 is useful here in this implementation. Why? Because it is free from overflow. You can use this here. Mid is equal to L plus R divided by 2. Instead of L plus R divided by 2, you can use this implementation. This will not overflow and it will always be in the range of L comma R. But the thing is, it is this is not exactly the definition of midpoint, because as you can see here, when I did my range was 567 and I calculated L by 2 plus R by 2, it was always pointing towards 5, right? 5 divided by 2 plus 7 divided by 2, which is 7 divided by 2 is 3 and 5 divided by 2 is 2. So 2 plus 3, which is 5, and it was again pointing toward this variable. So if I am calculating L by 2 mid here, it will be wrong in this case. L by 2 plus R by 2 is wrong in this implementation. But obviously, no one chooses this L by 2 plus R by 2. This is just fancy implementation. You can choose if your implementation, like I am assuming most of the people here use this implementation, I guess, right? While L is less than equal to R, mid is equal to L plus R divided by 2. So this is the common implementation by people. So you can choose this also for you guys. L divided by 2 plus R divided by 2. It's safe because you don't need to write brackets and all that. Okay, we don't write bracket anyway. नहीं ना, we write ना L plus R divided by 2. L plus R divided by 2. Not bracket. In this case, we don't need to write brackets. Cool. So this is the one. This is the another implementation you can choose. What else was we need to discuss? Acha, monotonicity, predicate, and queries. Invariant is also no? Okay. So okay, just understand invariant as something that never changes, right? So the moment I chose this boundary, oh sorry, this invariant while L is less than equal to R, it means throughout the process, throughout all the loop, this portion is same. But I don't think we should discuss invariant more, because invariant is more useful in terms of competitive programming, that if you are choosing on tree, like if you are doing operations of tree on edges, and let's say you are zoring it with v, then in that case you are kind of doing the same operation, and invariant lies in that case. Or you are doing plus one minus one on array, so in that case sum is constant. Hence, like, discussing invariant in binary search is time waste, I guess. So we'll not discuss much, but we will discuss predicate. Why predicate is useful? Because in binary search you won't get necessarily the sorted array. The most of the tasks are complex, and what you need to do is separate out the concerns. Even in your interviews, you need to separate out those portion uh, that could affect your code. So most of the code, you shouldn't write like this, that while loop and then calculation of mid here, and then if calculation of mid wala portion should be separate out here, and the calculate portion should be here. Calculate mid, whether it's one or two true, like whether it returns true or false, this calculate mid portion should be separated out from the binary search wala portion. So we call this portion as predicate. Why predicate? Because it returns 0 or 1, right? So if calculate mid is 1, then whatever your binary search wala common logic, else the second logic, something like this. So this is the use of predicate, and most of the cases we deal with monotonic function. So many people were asking in queries what exactly the monotonous function. Uh, Monotonous function is, you can say, non-increasing decreasing function, but mostly yeah, non-increasing decreasing you could say. So you can apply the binary search portion because our binary search relies on some space, right? I also wanted to cover some more complex cases, but I don't think we have enough time for that. Uh, so I will add it to our practice task PDF, or that I will provide to you later. Okay, so predicate is just the Boolean value for the nested portion or the part that we use for calculation. By the way, this is not the complete binary search session. This is just the implementation session. What are the various implementation? Hence, I'm not discussing this much in this stuff in detail. Else, I would have gone in much detail for this. So predicate will be always be 0 and 1 for this thing. L equal to 5, I equal to 6. Okay. I'm so obsessed with that 4, 5, 6 to handle edge cases. Anyway, the condition inside invariant is done. Monotonicity, I will also define the monotonicity. Monotonous function is basically which returns non-increasing, either non-increasing or non-decreasing. Any nature of function is monotonous. So this portion is monotonous, right? This, this, even if it is a non-differentiable graph, if it is like this, if it is increasing always or non-decreasing, basically not, you are not getting some value, something like this. So if it is not the case, you can always binary search. You can see my value is always incrementing, like, see why this value is getting incremented by 1 and 1. This is my graph. I have not chosen this properly, but something like this, or like this. You can binary search this also. So why this is useful? Because if you wanna search this search space, you can eliminate half portion here, right? So here, whatever value is there, you can eliminate that. And this is a symmetric graph, by the way. Like, so if you eliminate this portion, you will eliminate the entire nature of that graph. Like, what I wanted to say was, even though I am partitioning here, my binary search is not on this portion. My binary search is on this one. This is what I'm binary searching on, right? That whether the value is less than equal to 3 or not, whether the value is 4 equal to not. So this is basically index x-axis, and this is the value, which is the array values. So I am binary searching on the values, not indexes, right? But indexes are kind of incremented using that. So hence, anyway, like this is might be confusing for you. So you just need to remember this thing. Remember this, and this is the definition of monotonous. You can use binary search on that. So I think if we cover ternary search, it will waste more time. Instead, what I will do is instead of covering ternary search, I will show you one trick that will be used for ternary search graph. So ternary search graph is something like this. Ternary search, right? So if ternary search graph is something like this, or something like this, any portion you can take, right? So if it is something like this, binary search won't work exactly, because for binary search we need either increasing array or decreasing array, right? So we can decide to go toward left or right. But here in this case, you can get the same value. So what we'll try to do is we will use the mathematical trick on this. We will not apply ternary search. I never use ternary search on this kind of graphs. What I try to do is I kind of like see, if you see that slope here is, first it is decreasing slope. You can see here it is increasing slope. If you draw the tangent to this graph, it is always increasing. So we know that our binary search will work on increasing graph. So what we will try to do is to find the peak, which is basically m equal to 0, or the slope equal to 0. All you need to do is binary search on that slope. So you will try to find value at this instance and value at the next instance, and check if it is increasing or not, something like that, with the previous value. So you can choose initial m equal to minus infinity, and then see if it is increasing or not, if you are at here, and see if you want to try to find the peak or not, something like that, and to go towards right or left based on that. So yeah, this is the trick. Because we are short on time, I don't think we can cover ternary search much or this much. I will cover only the queries of people. Hmm. Okay, let me either uh, अरे हाँ, the sentinel value वाला case is remaining. Why? हाँ, this one. So if r minus l, the two number stopping wala case is there, and why I could choose l equal to minus 1, like so many people ask me this. L equal to minus 1 and r equal to n. How does this work exactly? Even if, because usually our goal is to choose the numbers in like 0 to n minus 1, right? But how, even if I chose l equal to minus 1 and r equal to n, why my numbers are still valid, right? So usually what we try to do is, these are called sentinel values. So let's say you want to try to calculate the prefix sum, and what, instead of adding extra condition just to handle the case of 0, like prefix of I equal to prefix of I minus 1, right? So because we know I is dependent on I minus 1, so when we are at 0, 0 is dependent on minus 1. So instead of adding this minus 1 condition, because obviously minus 1 can't be my index, right? So what I will try to do is use this as a virtual index, right? So either you can use hash map or like something like that, but here these are just because this is a search space, right? This is search space, so we don't care. All we need to do, we know, if we know our array is something like this, 0 0 1 1 1. So many times your binary search will not cover cases like this, that entire predicate is 0 0 0, predicate range is 0 0 0 or 1 1 1 1 1, depending on implementation. So sometimes these cases are not handled by binary search, right? So most of the cases we assume our range are something like this, that either it is 0 or 1. So how to handle these cases? So what we'll try to do is add another 0 and 1 to the end. So whatever the range is, I will add another 0 and 1 here, right? 0 and 1, because it will not disturb the monotonicity. It will not disturb the monotonicity, like 0 and 1 are still there, and you can still search the boundary, right? But what happens if I need to find the first instance of one? So I will end up here. But because I know my R boundary has R equal to N, and I know N is not a valid index for R. So I know this array has no one index. That's it. Hence, L equal to minus 1 and R equal to N works. Reason one, that because first thing, it will always give value between minus 1 to N, and also these are basically virtual indexes. Those are not part of a array, but those are part that will not break the monotonicity, and you can just search on that, something like that. So yeah, this will work because these are sentinel values basically. uh, the decimal portion. So what if you need to search on decimal? So usually the comparison between decimals is different. So if you want to compare a decimal, it's something while R minus L less than some error. And what this error is, it should 10 raised to minus 6 or whatever precision you need, you can do that. So instead of while L less than R, all you try to do is the difference between L and R, because it is stopped at L equal to R, right? But this doesn't work on double value or decimal value, because in decimal comparison is not possible, because the store how decimals are stored are very different than integers. If you have any query, you can ask, by the way. Put it in the chat. Query 2, Sentinel values. This is the double wala portion, that if you want to compare two double values, you can compare it L equal to R. This doesn't work in programming. You all you need to do is assume that L is less than R and choose R minus L equal to very small number, which is error basically, or less than equal to error. Not equal to this, equal to doesn't work. Less than equal to error. So it means, or in mathematical terms, it just means that the you might have seen this, right? Like x plus h equal to x, something like that, tends to limit wala thing. It's the same thing, but in programming, that R minus L, R equal to L plus error. So this error is taking care of all the. This is basically less than equal to, but the difference between these two numbers is very small, that we are considering them as equal, because we can't directly compare double values. So by the same logic, you can use binary search. Instead of integers, now you can use double value, that double L equal to whatever double R, and then choose the same binary search. Let me check the chat. Sculpt here.
Yes.
Uh, uh, what the query did you have, like with the binary search within decimal?
Uh, let's say, for example, you just explained that we just increment the range or decrement the range by +1 or -1.
Plus one or minus one.
Right.
Which example? Like the common
In,
template?
yeah, in any example.
Mm,
Consider any example. I just have doubt that actually I've encountered one question on code forces only. I don't remember the question, but in that particular question, they were not doing +1 or -1. Instead, they were doing plus of 0.0001 and minus of 0.0001. So initially, what I
Usually we do something like that only, no? Like so you are depends, like it's very task dependent. Like usually if you want to get your precision to a 10 is to minus 6, like
hmm,
whatever the actual answer, There is also CSCS question on this, that you can directly calculate the answer to, like, the CSCS task wanted to they wanted your answer to be exactly precise towards that 10 is to minus 6. Like those 6 digits should be equal with the actual values, right? And turns out the task was too difficult for anyway, like it will waste time. um, okay, so 10 raised to minus 6 ka range we need, right? And so most, why, there is some reason, complex reason, which I will won't discuss because it will take time. So answer equal to 10 raised to minus 6 is our, why we chose always that our answer minus the actual answer or the judge answer should be, absolute value of this should be less than equal to error, basically something like this. So this is the one that they need. So all you need to do is try to calculate our answer to close to our actual answer, right? So if it is 10 raised to minus 6 and you have got your range to 0 to 1, so like the decimal part you got to 0 to 1, now you can just do the 0.0 plus 1 wala difference. I don't know what binary search version you saw. I never saw it plus 0 1 minus 1 wala thing, but something like this decimal wala portion. Like decimal wala portion, L equal to mid, R equal to mid always works. Doesn't matter whatever version you are choosing, because there is no plus one minus one wala error in double na. So you can always choose this thing, that if you got true, L equal to mid, else R equal to mid, because all you need to go towards this portion, that this is 0 0 0 0, and you need to reach that zero wala portion. And obviously this is a continuous function in double. Like in when we are dealing with integer, we know that this is 1 2 3 4 5, but in double we know that this is a continuous graph which is 0 0 0 0 0, and which is 1, and you need to find this. Mostly polynomial values we deal with, that if you need to find the root of that, so we use double values on that. But I guess this is the template. I don't know where you saw this 0001 wala case. It doesn't make sense to add it here, because this will work. L equal to mid, else R equal to mid.
No, I'm talking about subtracting from R only. If it is true, then we'll keep L equals to mid. Otherwise, what we'll do is R equals to mid minus 0 point some zeros and then 0.1 like that.
अच्छा मतलब mid minus h or error ना.
हाँ
Not error, basically that's a maximum allowed portion to us.
हाँ मतलब
So small
मेरा
portion.
डाउट वही है कि अगर हमने इधर देखो आपने इधर 0.000 देन 1 लगा है लिखा है सो व्हाट आई डिड इज दैट आई जस्ट डिड माइनस 0.1 सो
हाँ
इट
हाँ,
वाज
अरे both portion are safe. See, what our end goal was to reduce the search space, right? It was L comma R. So if we got the true value, we did it L, and if we got the R value, then instead of doing minus one, all we could do is minus H, na? Because that, but all this doesn't make any sense, because this is costing us a lot of operations to do minus 0.001, because uh, with doubles this operation is costly to do R minus H, basically. So why to do R minus H when you can just put R to mid basically na? So we don't need to do that thing, because we know at mid calculation, if we get the false value, so we need to move towards left, and so in the end we will always go towards L equal to R, right? So this is the main target. So doing this uh, kind of like you think it is faster, because we are kind of like reducing our operations by in each iteration, but it's not, like it's costly instead. For your question, what you are asking, why we are subtracting minus h, basically this is the range L comma R, right? So if you got false here, if you got true here, and so whatever false portion is there, if we got false, we know that like this is useless to us. So instead of doing L equal to mid plus 1, I am choosing that I will choose something later than that, obviously, because this is current, the current portion is useless to us. So I will choose something later than that, and which is plus h.
And how do we decide the value of h? Like, should we cap it to 0.1 or 0.001?
Depends like what precision you need. If it is asked that it is 10 to minus 6, then you will add plus h.
Oh, okay. So the basically we just simply add the precision which is given in the question only, no?
Like you can also use 10 to minus 7, but I think it is useless. Most of the double cases you can just use L equal to mid if true, like whatever. If it is 11100, then if true, mid, else R equal to mid.
So that way it will be getting into the infinite loop, no?
नहीं infinite loop होगा नहीं ना, because what will happen if true L equal to mid, but our portion is while R minus L is sorry greater than error. So we are kind of shrinking our range at each instance. So divide by 2, divide by 2, divide by 2. Our range is getting shrink. The L by 2, L plus R divided by 2 always.
Okay, but and when the while loop ends, L and R will be pointing to two different values, right?
Usually double always point to a different value, even though like they loop same, but double will always point to a different value. So all we need to do is make sure that our absolute error is very less between those two values.
Mhm. Okay.
Okay. Mm, let's move to more questions. I am skipping the ternary search because I guess it. Mhm. Monotonicity we discuss. Ternary search for a question mostly queries. Ternary search is also same, by the way, if you guys want to understand that we will move towards a certain direction. But anyways, I will skip that because it's already long session. Any other query by other people? Okay, then I will try to stop the recording. You can ask off recording also. Manage recording.